let's see if we can apply some of our new tools to solve some line integrals. So let's say we have a line integral along a closed curve. I'm going to define the path in a second, of x squared plus y squared times dx plus 2xy times dy. And then our curve C is going to be defined by the parameterization x is equal to cosine of t, and y is equal to sine of t. And this is valid for t between 0 and 2 pi. So this is essentially a circle, a unit circle in the xy plane. And we know how to solve these. But let's see if we can use some of our discoveries in the last couple of videos to maybe simplify this process. So the first thing you might say, hey, geez, Sal, is it, this looks like a line integral, but you have a dx and dy. I don't see a dot dr here. It's not clear to me that this is some type of even a vector line integral. I don't see any vectors. And what I want to do first, and the reason why I wanted to show you this example, is just to show you that this is just another form of writing really a vector line integral. And to show you that, you just have to realize if I have some r of t, this is our curve. And I won't even write these functions in there. I'm just going to write it's x of t times I plus y of t times j. We've seen several videos now that we can write dr dt as being equal to dx dt times I plus dy dt times j. We've seen this multiple times. And we've seen multiple times we want to get the differential dr. We could just multiply everything times dt. And normally, I just put a dt here and a dt there and get rid of this dt. But if you multiply everything times dt, if you view this as the differentials as actual numbers you can multiply, and normally you can treat them like that, then you just get rid of all of the dt. So dr, you can imagine, is equal to dx times the unit vector I plus dy times the unit vector j. So put that aside, and you might already see a pattern here. So if we define our vector field f of xy as being equal to x squared plus y squared I plus 2xyj, what is this thing? What is this thing over here? Well, what is f dot dr going to be? Dot products, you just multiply the corresponding components of our vectors and then add them up. So it's going to be, if you take this f and dot it with that dr, you're going to get the I component, x squared plus y squared times that dx plus, do it in the pink again, plus the y component, the j component, 2xy times that dy. That's the dot product. And notice, this thing right here, that thing right here, is identical to that thing right there. So our line integral, just to put it in a form that we're familiar with, this is the same exact thing as the line integral over this curve C, this closed curve C, of this f, maybe I'll write in that magenta color, or that, actually it's more of a purple or a pink color, f dot this dr. That's what this line integral is. It's just a different way of writing. And now that you've seen it, in the future, if you see it in kind of this differential form, you'll immediately know, okay, there's one vector field that this is its x component, this is its y component, dotting with dr, which this is the x component of dr, or the I component, and this is the y component, or the j component of the dr. So you immediately know what the vector field is that we're taking a line integral of. This is the x, that's the y. Now, let's ask ourselves a question. Is f conservative? So is f equal to the gradient of some scalar field, we'll call it capital F? Is this the case? So let's assume it is, and see if we can solve for a scalar field whose gradient really is f. Then we know that f is conservative. And then if f is conservative, and this is the whole reason we want to do it, that means that any closed loop any line integral over a closed curve of f is going to be equal to 0, and we'd be done. So if we can show this, then the answer to this question, or this question, is going to be 0. We don't even have to mess with the cosine of t's and the sine of t's and all of that. And actually, we don't even have to take antiderivatives. So let's see if we can find an f whose gradient is equal to that right there. Whose gradient is equal to that right there. So in order for f's gradient to be that, that means that the partial derivative of our capital F with respect to x has got to be equal to that right there. Right? It's got to be equal to x squared plus y squared. And it also tells us that the partial derivative of capital F, with respect to y, has got to be equal to 2xy. It's got to be equal to 2xy. And just as a review, if I have the gradient of any function of any scalar field is equal to the partial of f with respect to x times I plus the partial of capital F with respect to y times j. So that's why I'm just pattern matching. I'm just saying, well, gee, if this is the gradient of that, then this must be that, which I wrote down right here. And this must be that, which I wrote down here. So let's see if I can find an f that satisfies both of these constraints. So we can just take the antiderivative with respect to x on both sides. And if we take the antiderivative with respect to x on both sides, remember, you just treat y like a constant, or y squared like a constant. It's just a number. So then we could say that f is equal to the antiderivative of x squared is x to the third over 3. X to the third over 3. And then the antiderivative of y squared, remember, this is with respect to x. So you just treat it like a number. That could just be the number k. Or this could be the number 5. So this is just going to be that times x. So plus x times y squared. And then there could be some function of y here. So plus some, I don't know, I'll call it, g of y. Because there could have been some function of y here when you take, if it's a pure function of y, when you take the derivative or the partial with respect to x, this would have disappeared. So it would reappear when you take the antiderivative. And let me, just to be clear, let me make it clear that f is going to be a function of x and y. So this, we just took the, I guess you could say the antiderivative with respect to x. Let's see if we take the antiderivative with respect to y, and then we can reconcile the two. So based on this, f of xy is going to have to look like, so let's take the antiderivative with respect to y here. So remember, you just treat x like it's just some number. It could be a k, it could be an m, it could be a 5. It's just some number. So if x is just some, the antiderivative of 2y is y squared. And if x is just a number there, the antiderivative of this with respect to y is just going to be x y squared. Don't believe me? Take the partial of this with respect to y. Treat x like a constant. You'll get 2 times xy. And then there's no exponent there. And of course, since we took the antiderivative with respect to x, there might be some function of x here. We were just basing it off of that information. Now, given that, this information says f of xy is going to have to look something like this. This information tells us f of xy is going to have to look something like that. Let's see if there is an f of xy that looks like both of them, essentially. So let's see. We have, on this one, we have xy squared here. We have an xy squared there. So good. That looks good. And then over here, we have an f of x. We have something that's a pure function of x. And here we have something that is a pure function of x. So these two things could be the same thing. And then here we have a pure function of y that might be there, but it didn't really show up anywhere over here. So we could just say, hey, that's going to be 0. 0 is a pure function of y. You could have something called g of y is equal to 0. And then we get that f, capital F of xy is equal to x to the third over 3 plus xy squared. And the gradient of this is going to be equal to f. And we've already established that, but just to hit the point home, let's take the gradient of it. Just so you don't believe this little stuff that I did right there, let's take the gradient. The gradient of f is equal to, and sometimes people put a little vector there because you're getting a vector out of it. A little vector on top of that gradient is fine. The gradient of f is going to be what? The partial of this with respect to x times I. So the partial of this with respect to x, the derivative here is 3 divided by 3 is 1, so it's just x squared plus the derivative of this with respect to x is y squared times I plus the partial with respect to y. Well, the partial with respect to y of this is 0. Partial with respect to y of this is 2xy, or 2xy to the first. So it's 2xy times j. And this is exactly equal to f, our f that we wrote up there. So we've established that f can definitely be written. F is definitely the gradient of some potential scalar function there. So f is conservative, and that tells us that this closed loop integral, line integral of f is going to be equal to 0. We are done. We could even ignore the actual parameterization of the path.